So in photochemistry, we introduce what is photochemistry of carbonyl compounds starting from photoreduction. Then we also discuss pattern of Buch reaction. Then we also introduce what is Nourish 1. So Nourish 1 is that one where you can cleave alpha bond, and finally there is a responsibility to give alkyl as, and one more is acyl radical. So three ways of stabilizing the corresponding radical. Transfer of hydrogen from alkyl to acyl, one I explained. Next is acyl to alkyl. Then decarbonylation at loss, carbon intermediate formation takes place. They are the three possible stabilizations of Nourish 1. Next, fourth point in characteristics. Right. Here, always Nourish 1 proceeds through stable alkyl radical. Whichever direction we are getting a stable alkyl radical, from that direction it will take place. Suppose if any unsymmetric ketone is present or unsymmetric carbonyl is present, whichever side stable radical come, from that side Nourish 1 is possible. So always Nourish 1 proceeds through stable radical formation. Stable and especially alkyl radical formation. Suppose see, if I take methyl and ethyl, right side methyl, left side ethyl is there. Suppose if I make photochemically, left side it is possible to cleave. If I cleave left side, what is the radical? Ethyl radical. And what is one more? CH3 C double bond O is acyl radical. So now this is found to be stable. Suppose see, if I make photocleavage towards right side, now you will get acyl radical like this, then followed by methyl radical. So this is found to be unstable. Whichever side we are getting more stable radical. See, alkyl radical is more stable if you cleave this side. Now alkyl radical is unstable if you cleave right side. Which is better? Left side is better. So always cleave that side where you will get a stable radical. What is the stability out of radicals? Tertiary, secondary and primary. Now it is a primary and this is super primary. So I can say this is more stable as compared to this one. That's why this direction is predominant. So this is A cleavage and this is B cleavage. Which cleavage is preferred? A cleavage is preferred in Nourish 1. Suppose see, left side isopropyl I taken, right side ethyl I taken. So which side you will cleave? Photochemically. Left side, because left side you will get isopropyl radical. Then there is a formation of acyl radical like this. So whichever side have a tendency to give a stable radical, that side Nourish 1 is possible. Clear? Left side is primary, right side is super primary. Left side is secondary, right side is primary. So secondary radical is more stable as compared to primary. That's why right side cleavage is not exist. So if any unsymmetric ketone is given, Nourish 1 is takes place toward that side where you will get a stable radical. Alkyl radical should be stable. Only that direction Nourish 1 is possible. Right. So what are the intermediates involved in Nourish 1? Acyl radical and alkyl radical. Suppose if both are same, left side, right side both are same, no problem at all. But whenever if unsymmetric ketone is given, Nourish 1 cleavage towards that side where you will get a stable alkyl radical. It depends on this one. This is stable, that's why left side is cleaved. Suppose if right side is more stable, right side is going to be cleaved. So what is Nourish cleavage? Cleaving sigma bond present between alpha carbon and carbonyl carbon. That is Nourish 1. Okay, next. Now fifth one. See, Nourish 1 does not exist between carbonyl carbon and carbonyl carbon with adjacent sp2 carbon. sp2 or sp carbon. So Nourish 1 cleavage is not possible when double bond is connected to carbonyl. That side Nourish 1 is not possible. Nourish 1 does not exist when carbonyl compound is attaches to adjacent sp2 carbon or sp carbon, which means, so if I write a double bond directly attaches to carbonyl, okay, so this side Narish one is not possible, other side possible because it is sp2. So if it is sp3, this side possible, okay. So photochemically Narish one is not possible towards left side, but right side it is possible. And here carbon carbon triple bond is present, C double bond OR. Now see, this is a sigma bond present between alpha carbon and carbonyl. Now this is sp hybridized carbon. Here Narish one is not possible this side. If carbonyl carbon adjacent, if any sp2 carbon or sp carbon directly connected to carbonyl, even though it is alpha carbon, Narish one is not possible, other direction possible. See, this side possible, this side it is possible. So Narish one is not exist between this carbon and this carbon. And even suppose if I take any aromatic ring, this is C double bond OR. So photochemically, can I cleave this side? No, because what is the hybridization of benzene? sp2. So that's why this side is not possible. Right side it is possible. Clear? Always remember, if carbonyl adjacent is sp2 carbon or carbonyl adjacent is sp carbon, Narish one is not takes place toward that side, opposite side is possible. If this carbon is sp3, suppose if this carbon is one more time sp2 or sp, so there is no complete Narish one in that molecule. Suppose if I take benzophenone, AR C double bond O AR, so around this particular carbon, is it sp2 or not? Benzene sp2 hybridization, it is also sp2. So Narish one is not possible in any direction. It is not possible, and here also it is not possible. So what is the primary requirement for Narish one? Adjacent alpha carbon should be always saturated. If this carbon is saturated, carbonyl adjacent carbon, if this carbon is saturated, then only Narish one is possible. This is saturate, all are saturated. So that's why right side is possible, left side is not possible. Suppose right side, left side both are unsaturated, no reaction. Narish one is not completely exist. Here what I am saying is, whichever side alpha carbon is sp3, only that side it is possible. Suppose if two adjacent sp3s are present, whichever sp3 will give stable radical, only that side Narish one is possible. See, in this one, it is sp3 or not? sp3. And what about here? It is also sp3. Both sides sp3 is there. So both side cleavage is possible. Left side I am predominating because it is giving a stable radical. Suppose left side is sp2, right side sp3 is there, blindly go for sp3. So next, see, in gaseous state or vapor state, both are same. In gaseous state, vapor state, decarbonylation is predominant reaction. So here you need to remember this point. Narish one, in gaseous phase, what is the reaction? First is remove CO, that is major. So these are the key points which you required. In gaseous state or vapor state, decarbonylation is predominant in Narish one. If they mention gaseous phase, if they not mention gaseous phase also, this is dominate. Okay. Suppose see, in solution state, solution state or liquid state. If solution or liquid state is given, okay, transfer of hydrogen from alkyl to alkyl radical, this is alkyl radical to which one? Alkyl radical to acyl radical is predominate. It is a predominant reaction. Okay. If solution state is given, transfer of hydrogen takes place from alkyl radical to acyl. That is a dominating reaction. Solution is given. Okay. And third one, if solvent is given, especially polar solvent, mostly they will give alcohol. Clear alcohol is mentioned. Okay. If solvent is given, reaction proceed with carbene intermediate, carbene and one more, carbene ketene intermediate. So here there is a variation, is it, that I will show. So this point you need to remember. These 3 points will decide the answer. Nourish one. If they mention gaseous phase, first to remove CO. Remove CO, removing CO is nothing but decarbonylation. And suppose if solution state is given, transfer of hydrogen takes place from alkyl radical to acyl radical. If solution is mentioned. Suppose solution state with solvent is mentioned. Solution is mentioned, suppose if they mention only solution, you write this answer. If they mention methanol, ethanol like that, on that time reaction proceed with either carbene intermediate and one more is ketene intermediate. Ketene nothing but transfer of hydrogen from acyl to alkyl. That point I given, acyl to alkyl. So after getting ketene, that ketene reacts with alcohol. Okay. Suppose here two reactions are possible here. Remember, when solvent methanol, ethanol is given clearly, photochemical below methanol is given. Don't write these two answers. You follow carbene intermediate, otherwise ketene intermediate. Two are possible. Okay, so out of these two, which is major, I will show. Okay, remember two products, ketene product, one more is what? Ketene intermediate. See the reaction. I am giving acetone. Acetone on photochemically irradiated. Then see, there is a formation of ketene. And there is a formation of methane. And there is a dimerization product is possible. These are the nourishment products. When acetone on photolysis, nourishment products are ketene, methane and what is this? Ketene, methane and ethane, dimer product. Okay. So, what are the intermediates exist in this one? Transition state is. What is the reaction transition state? Singlet and triplet. But triplet is predominant. So, photochemically what happens? See, this will give singlet. So, N2 pi star singlet, N2 pi star triplet is also possible. But most of the aliphatic are not effective ISC. But it may be singlet or triplet, your answer remains same. But triplet is more effective as compared to singlet. Now what happens? See, this will give nourish one. Cleave this. After cleaving here, there is a formation of acyl radical and alkyl radical. See, is this alkyl adjacent any carbon is there? Is this alkyl adjacent any other carbon? No. So there is no transfer of hydrogen from alkyl to acyl possible. Not possible. Okay. So then transfer of hydrogen takes place from acyl to alkyl. Only this is possible. So break this hydrogen migrate from here to here. Now this radical forms double bond and this is ketene. This hydrogen transfer here, your answer is methane. See, this two product formation takes place after nourish one cleavage. There is a transfer of hydrogen takes place from acyl to alkyl. there is no transfer of hydrogen takes place from alkyl to acyl. Why? Why hydrogen cannot transfer from alkyl to acyl? Reason is alkyl adjacent carbon there is no one more carbon. So that's why they never donate hydrogen to this one. If there is no possibility of transferring hydrogen from alkyl to acyl, then go for transfer of hydrogen from acyl to alkyl. Clear? So now it is donating hydrogen. It is accepting hydrogen or not? So hydrogen donor is A. Loss of hydrogen is called oxidation. Gain of hydrogen is called reduction. So now these two are disproportionation reaction. This is a disproportionation. Oxidation and reduction. Self-oxidation, self-reduction is called disproportionation. Okay. Now this molecule also undergo decarbonylation. See, when you remove two equally possible or not? Two equally possible. If I remove CO, then how many methyl radicals you are going to get? Two methyl radicals. Two methyl radicals, when they combine together, then there is a formation of dimer. So there is a formation of dimerization, then there is a formation of decarbonylation. So this is major, this is minor. Three reactions are common: disproportionation, decarbonylation, dimerization. Dimerization also very weak, but this is more effective. Loss of CO is a primary fragmentation. When vapor state is mentioned, see, physical state is not mentioned. In your exam, if physical state is not mentioned, try to take vapor phase, otherwise gaseous phase. So what are the three common reactions? Decarbonylation, disproportionation, dimerization. Start with 3D. D start with D, decarbonylation, most familiar. Then followed by disproportionation. When acyl transfer hydrogen to alkyl, or else alkyl transfer hydrogen to acyl, that reactions are called disproportionation reactions. Then finally dimerization. After decarbonylation they may undergo dimerization. Dimerization never takes place without decarbonylation. See, I want to make dimer. These two methyls I want to combine together. Okay, this is possible only when if I remove CO. Loss of CO is nothing but decarbonylation. If physical state is not mentioned, think about vapor phase only. One question is compulsory from either nourish 1 or nourish 2. Otherwise any combined question with pattern of Bucci. These are very standard reactions. Oxo-dipymethane rearrangement, dipymethane rearrangement, photooxidation, photoreduction, okay, then photochemical reactions of pattern of Bucci, photofreeze rearrangement also there, one name reaction, photofreeze. So what is the actual state for nourish 1, N2 pi star singlet or triplet? Both are possible. Effective is triplet only. N2 pi star triplet is the most effective state for nourish 1. Now see the applications. See, this is a photochemical reaction. This is vapor phase. vapor phase or gaseous phase they will mention. Now this is under photochemically irradiated, nourished one. So both are same or not? This bond, both are same. First vapor phase is given, go for decarbonylation. If I remove CO after photochemical irradiation, what is removed here? Loss of CO. Then you will get biradical or not? Now these two radicals are combined together and forms cyclobutane. These two radicals one more time undergo cleavage and forms two olefins. Your answer is proceed with decarbonylation, loss of CO. But this is minor, this is major because strain ring. Okay? So always see, after removing CO, these two radicals combine and form CO. These two radicals are left on this carbon. And see, these two radicals combine together and forms 4-membered. This radical if you break, forms double bond and you will get two olefins. Okay? Suppose if I put any double bond over here. So same, photochemical, this state. Now, what is your answer? Can I remove these two radicals? Remove this. Now loss of CO. Then break this bond homolytically. Then what happens? See, double bond, that is the answer. Break this double bond, this radical, double bond, this and this double bond, that is the answer. But ultimately is it decarbonylation or not? Loss of CO followed by stable product. Okay? So, suppose if I write a 3-membered ring here. This is C double bond O. Now photochemical irradiated. See, break this bond and see I got two radicals. Now break this. If I break this, what happens? This radical double bond and 3-membered ring as it is. This radical double bond. Then later on what happens? See, this is unstable. This hydrogen involved in tautomerism any side. This side and it will migrate like this. So on the time, this is double bond, this is your final answer. See, what is the common thing you observed? Loss of CO. Here physical state is gaseous. Here also gaseous state or vapor state. If state is not mentioned, apply gaseous state. Because under gaseous state, reaction is more efficient. Okay? So loss of CO, final answer is a stable product. Final answer is stable product. Don't think only one product is major every time. That depends upon the skeleton rearrangement. Here double bond is a, that's why this is major. Here there is no double bond inside. Ring formation is unstable. Opening product. That's why it's called photocleavages. So break this one, you will get double bond. This and this you will get one more double bond. Total how many double bonds here? Two olefins are going to be obtained. Carbon double bond like this. So ultimately where we are cleaving? We are cleaving between carbonyl and alpha or not? And here also carbonyl alpha. So I am cleaving two bonds. Left side, right side bond both are equal. That's why I am cleaving two. So that's why see in last case also here I am cleaving. Left side, right side both I am cleaving. I am removing CO. I am saying this is major. Clear? Right. This is tautomerism. Shift of proton is called tautomerism. Finally you will get stable conjugate product. Stable conjugate product is major. So give the answer for this. This is C double bond O. 1 2 1 2 and it will be connected. Photochemically, what is the answer? So if more than one double bond is present, photochemically C double bond O, C double bond O, photochemically what is the answer? If adjacent carbon having sp3 without having gamma carbon, most probably it is Norris 1. Decarbonylation. Is it a decarbonylation or not? Yes. Decarbonylation everywhere. Decarbonylation reaction. So break this bond. So after breaking this bond, combine these two radicals. Remove CO, combine the two. If I combine, what will you expect? 1 2 3 4 5 6. So that is the answer. So what is removed out? CO is removed out in gas phase. These two radicals combine, these two radicals form CO. Okay? And here see, first you remove these two. If I remove these two, here tertiary butyl CO is there. One more time if you remove this one, then there is a formation of a trans. First one CO, back to back CO, decarbonylation. And here also same. First you remove these two. If I remove this, double bond, here tertiary butyl. So loss of CO. One more time loss of CO, then double bond, tertiary butyl. Back to back loss of COs. So state they won't mention, that is gaseous phase only. Over. So when more than one carbonyls are present, go for back-to-back decarbonylation, and finally you will get a olefin that becomes a trans olefin. So here this is C double bond O. Photochemical loss of CO. So break this and break this side, and loss of CO will give this answer. So this one remains same, and this bond will be connected. This is called prismane. Loss of CO, this radical combine together and form single bond. So this is benzene, photochemical. What is the answer? So different products are expected in this one. That depends on stability. See, break this. After breaking, what happens? You will get benzyl radical. So now these two units are get combined together and forms a dimer. This is the final answer. Dimer is the answer. Okay. So two decarbonylations are going to take. So here two methyls are given photochemically. What is the answer? Here 2 units, this radical, they won't mention 2 units. You need to take based on stability. So remove CO. After removing CO, 2 alkyl radicals you will get. Alkyl radical or one more radical. Okay? And one of the alkyl radical will donate one hydrogen. So this hydrogen migrate here. Double bond methyl and here alkyl. You will get different answers in Nourish 1. Don't depend on one molecule. So if I take phenyl and here one more phenyl. So initially photochemical, if you irradiate, there is a loss of CO takes place. Here pH and this is pH, radical. These two combine together and forms this product. Here cyclation possible because you will get a stable radicals. Whatever intermediate radicals you are getting, these two attach directly. Here it is not possible because this radical stabilized by this phenyl, this radical stabilized by this phenyl. So lifetime increases. When lifetime increases, these two radicals will combine. So if substitutions are present here, then only it is possible. This is major. Here radical having no phenyl ring, dimer possible. But still see, first I removed CO. Loss of CO is common every time. Decarbonylation. This is 5-member ring and here I am writing 2. CS3 and here CS3, CS3. Photochemically, what is the answer? Now break this, remove this and see, here will expect this kind of radical. Here radical and here radical. Now these two radicals will combine together and form say 4-membered. It is also possible, and here if you break this side, this radical, one double bond, and here same, one more double bond. Two products are expected. First loss of CO followed by back-to-back cleavages. Photochemically, what is your answer? They won't give CO. Physical state is not mentioned, means gaseous state. So first you need to create a biradical. Now this biradical undergoes cyclation. You may get a 5-membered ring. So after 5-membered ring, there is possibility of transferring hydrogen from here. So here put double bond like this. This radical join together, that is one answer. If you break this hydrogen, and if this hydrogen migrate from here to here, this radical double bond, and this hydrogen here, you will get saturation. So this is similar, just you work out this, same answer. Photochemically, what is the answer? This is tertiary butyl and here also tertiary butyl. What is the answer? Gas phase or vapor phase? Here pH and this is pH. Photochemically, what is the answer? 2, I am mixing these two. When two different carbonyls are combined together, nourished one is possible still. See in this one, what is your answer? Can I write 5-membered ring? And one more, this hydrogen transfer from here to here. Can I put double bond or not? Same answer, last one. Now here, first can I break these two? After breaking, how many radicals you are going to get? 2 radicals or not? 2 alkyl radicals. Then this hydrogen migrate from here to here. Break this hydrogen migrate from here to here. Now you will get hydrogen and double bond. So this radical you will get double bond. Now see 2 different or not? When 2 different is given, remove CO from first molecule. Remove CO from second molecule. Like this possible. Gaseous phase. Remove the 2, combine the 2. If I combine first partner, what is your answer? CH2, pH. What about second partner? Here pH and this is pH and here also pH and this is pH. And one more cross product is possible. CH2 carbon carry pH and this is pH. Remove CO, combine these two. Remove CO, combine these two. After removing these two COs, this combined with this one. That is this product. All are decarbonylation products. Cyclohexanone photochemically. So this is gas phase. When gas is given, now what is your answer? You will get two radicals or not, remove CO, right? After removing CO, these two combine together and forms a 5-membered. Then, if you break here, then see you will get two radicals. This radical forms double bond, right? And finally see, here one of the hydrogen atom is present. So, this hydrogen, if you break, this radical comes here and this two radical forms double bond. That is the answer. Total 3 products are possible. Okay? First is cyclopentane and normal double bond, CH3CH double bond like this. This is byproducts. All are possible. So this all are due to combination of these two, and break here you will get double bond. And after getting you will get 1, 3 biradical. 1, 3. Transfer this hydrogen here, put double bond, you will get this answer. This is gaseous phase common reaction. Now solution state or liquid state. So loss of CO not possible in liquid state. So means I can cleave only one side. If I cleave right side, you will get C double bond O, radical and radical. Nourish one, alpha cleavage. Then transfer this hydrogen from here to here. If I this hydrogen transfer double bond and you will get unsaturated aldehyde. Right? Transfer of hydrogen from alkyl to acyl in liquid state. In liquid state, hydrogen transfers from alkyl to acyl. You will get unsaturated and alkyl. So one more possibility is there, transfer of hydrogen from acyl to alkyl. Then what is your answer? Here you will expect ketene. But this is minor. If solvent is mentioned, solvent name is mentioned, on that time this is possible. But if they mention only liquid state, physical state is this one. This physical state is liquid means this is major and this is minor. Ketene formation is minor. So if you migrate this hydrogen, this and this form double bond, this hydrogen migrates from here to here. You will get that last answer. But if you migrate this hydrogen migrate from here to here, you will get double bond and aldehyde. Unsaturated aldehyde in liquid phase. Okay, so can I break right side? Right side will give stable. This is stable, acyl and alkyl. Then followed by C. This hydrogen transfer takes place. This migrate from here to here double bond and this methyl. That is major. Migrate this hydrogen from here to here. Transfer of hydrogen from alkyl to acyl. Put double bond here. And this hydrogen migrates here, you will get this hydrogen. Right. 2 methyls I am giving photochemically here liquid state. Here 2 methyls I am giving photochemical solution state. Four methyls I am giving. Give the product of this physical state is solution. Where should I break here? Can I break right side? Here you can break any one side. See, whenever if you take solution side, don't remove CO. If it is a gaseous phase, try to remove CO. That is the key point. If it is a gaseous phase, remove CO. If it is a solution state, try to break that side where you will get a stable alkyl radical. Right side stable or not? If right side is stable, here see, you will get two radical, radical, radical. Now, remove this hydrogen, migrate from here to here. So, here you will expect double bond and this is CHO. Now, here also remains same. I am writing directly. Here double bond, CHO methyl. This is aldehyde, 1, 2, 3, double bond and here 2 methyls. Simple, break one side, transfer hydrogen, you will get alkyl and aldehyde. Don't remove CO when solution state is mentioned. So this is given in CSR. What is the answer? Is it solution state or gaseous state? Solution state. Can I break on sp2 carbon or sp3 carbon? sp3. Can I break here? If I break here now, you will get two types of radicals. This is C double bond acyl radical and here alkyl radical. Here one of the hydrogen atom is present, break this. Transfer this hydrogen from here to here. Then what is your answer? This is C double bond OH. Then see, this radical forms a double bond and you will get this answer. This is the answer. This is CSR question as well as gate question. So it is important one. Nourish one, it is most important. Even without phenyl, your answer remains same. Suppose normal CH2 is present, put double bond here. Transfer of hydrogen followed by putting double bond. This is 4-membered ring. Photochemically, I am using diene at minus 78 degrees centigrade of temperature. What is your answer? So if I break here, you will get radical. You will get like this, radicals or not? Here one radical, you will get. Now this double bond will join here. So this double bond I am writing like this. Here double bond, this I am writing like this. So this combined with this combined with this by removing this. This is major. If diene is not given, decarbonylation is possible under gaseous phase. Now liquid phase, use this. This is nourish one product. Nourish one product. And one more. So here you will expect this kind of product. What is this product? Carbonyl combined with olefin forms a oxetane. Pattern-Bucci product. So when any unsaturated molecule is given with carbonyl compound, there is a competition with Pattern-Bucci. On that time, nourish one is major. Pattern-Bucci is minor. Because we are creating two strain rings at a time. Here ring expansion, strain is released. 4-membered becomes how much? 6-membered. But 4-membered giving how many 4-membered? 2 4-membered. Means we are increasing strain or not? But here 4-membered become 6-membered. And these two are coupled together. It is also nourish one. Nourish one means cleaving carbonyl carbon and alpha carbon. If you cleave this one, that is nourish one only. See, this molecule after cleaving here, now I got 2 radicals. These 2 radicals I got, right? Now this is a diene. Diene I am writing like this. This radical I am joining. So this radical and this radical if I join together, okay, this is responsible to give this one. Is it a nourish one? Yes. What is the meaning of nourish one? Nourish one means breaking C alpha and carbonyl bond. If you break that one, that is nourish one only. Don't think that removing CO, dimerization, that is not nourish one. That is a product obtained by nourish one. Product obtained by nourish one is not always fixed. That depends upon the stability of concerned products. Whichever direction is more favorable for getting a stable product, that direction, that fragmentation is responsible. So don't think that always loss of CO, always migrating hydrogen, that is major. So this is not nourish one. Transferring hydrogen is not nourish one. Breaking this bond is called nourish one. After breaking, this molecule attains stability in possible ways. Okay. So if this hydrogen transfer here, now both will be stable, that is called unsaturated carbonyl product. So this is not a nourish one product. Nourish one cleavage is expected, but nourish one product is not common. Remember, don't fix nourish one product is always constant. Nourish one cleavage is constant, but nourish one product is not constant. That depends upon the molecule. After cleaving, whichever direction it will attain stable product, that direction cleavages will be directed. Try to understand. That depends on molecule. After getting this intermediate, you will get further products. This product formation depends on stability. Whichever direction you get more stable of these 2 radical, that direction it will be directed. This one. This one you are asking. Pattern of Bucci you are asking. Pattern of Bucci. Second. This you are asking. This one. What is your problem? This substitution. Why not above? What is pattern of Bucci reaction? Yesterday I explained, na? Last before class, pattern of Bucci, all possible applications are given. So why not above you are asking? This is radical. If these two combine together, so this you are asking. Are you listening pattern of Bucci reaction last class? Are you absent? That you don't have any right to ask. If you present, you can. Pattern of Bucci multiple applications explain. See the last reaction in pattern of Bucci reaction. See, when olefin is electron rich, CC bond followed by CO bond. If electron is electron deficient, CC or CO, first CC followed by CO bond. This is your last class. From there onwards explain. Nourish, before starting Nourish 1 reaction, pattern of Bucci applications are given. So for this problem only. When any diene is given, internal radical will be a second coupling partner. Internal radical is a second coupling partner. First this bond formation takes place. When this bond formation takes place, double bond, radical, and these two radicals you will get. Biradicals are intermediates in pattern of Bucci reaction. Biradical. Suppose if it is only direct 1, 2 carbonyl, on that time it is C double bond O is going to couple. Okay? This formation is not pattern of Bucci reaction. It is Nourish 1. This is pattern of Bucci reaction. So in this one, see, when these two radicals are coupled together, this radical is stabilized by conjugation. Suppose if these two radicals are coupled together, now what about this radical? Is it a primary? Primary. Is it any stability factor for this radical? There is no conjugation first of all. Is it stable or unstable? Unstable. But what about here? This radical is stabilized by conjugation. So lifetime increases. Lifetime increases, slowly these two are coupled together. Suppose if lifetime is not there, these two not survive. Lifetime is very less, percentage is less. As lifetime increases, coupling interaction increases. More coupling interaction, more product. Here lifetime is very less. When lifetime is very less for unstable molecule, they will couple very fastly, yield is very less percentage. It is also possible, but what I am saying is yield is very less because they are produced with a unstable biradical. Okay, so this concept is almost all equal to your pattern of Bucci reaction only. Same way, last class I explained, see in your notes. Same, carbonyl whenever if it is combining, carbonyl group is combining with a conjugate partner, I combine this two and this two. Same reason, but there you are getting 1, 4, but here you will not get 1, 4, you will get biradicals only. Because our target is Nourish 1. Nourish 1 means cleaving alpha carbon and carbonyl carbon. You will get a biradical. So getting biradical between these two is called Nourish 1. Now Nourish 1 is over. Then what will be your next answer? Nourish 1 product depends upon corresponding stability of radicals. How these two radicals are stabilized? Adjacent one molecule is given, that's why it is using this molecule. Now it can use in two ways. You may get this product, you may get this product. Why you are getting this one? You will proceed with a stable radical. You are proceeding with a unstable, this is minor. So I am not writing this one. Is it clear? Generating stable radical is a ultimate target. Inner radical coupling, terminal radical coupling. Inner, if it is coupled, terminal is unable to stabilize by conjugation. That is the reason. Is it clear? Come regularly. If you miss one class, you won't follow me. Impossible. If you skip one class, I think you are absent in last class. That's why you are unable to recollect that point. You just revise that stereochemistry in pattern-Bucci. That is important one. Stereochemical aspects in pattern-Bucci reaction. N2 pi star singlet, N2 pi star triplet with aromatic and aliphatic to explain. Aliphatic is weak ISC, aromatic is effective ISC. There we are participating singlet, triplet. Relations also we discuss. Enhanced homers, diastereomers like that. ఏమే రావట్లేదా? వేడైందా? ఏంటి ప్రాబ్లం? వేడి అవుతుందా?